We're going to take a look at implicit differentiation now. So far we've looked at explicit differentiation. So here we have a function, and we're going to find its derivative, and we're finding that derivative with respect to x. And that's what we've been doing so far. But now if we get something, let's do something easy. Now we've got two variables, and I want to differentiate this with respect to x. So any place where the variable x occurs, it's the same as we normally do. So we've got 6x squared. Now for the 3y squared, we do a little something different. We have a chain rule. So first thing we do is take a derivative of 3y squared, which would look like that. But then we find this term, the derivative of y with respect to x. So we take the actual term here, find the derivative as we normally do, but we also need to say dy dx, or the derivative of y with respect to x. Now if we had something that looked like this, if we're going to differentiate with respect to x, x's worth the same, so we have 2x. Here again we have y, we have 2y times derivative of y with respect to x. Now this last term, it's a product, so x times y. So using our product rule, we'll take the first times the derivative of the second. So the derivative of y would be just 1 times derivative of y with respect to x. Plus, so first times the derivative of the second, plus the second times the derivative of the first. And then the derivative of the constant 5 is just 0. So any place where there's a variable other than the x's, we have to do this two-step, or this chain rule. So find the derivative of the y squared, just 2y, and then multiplied by derivative of y with respect to x. Now as this relates to related rates problems, so we've got, the area of a circle equals pi r squared. And we have a scenario where you drop a pebble into the water. And as we know, when you drop a pebble into the water, it forms rings which expand, they get bigger and bigger, the little ripple effect. So we want to find out how the area of the circle created by that. So you drop the pebble in, it creates a little circle. That circle has an area. As it expands, the area of that circle obviously gets bigger. So we want to find out how the area is changing as the radius is changing. So we know, let's say that when you drop the pebble in, radius changes at a rate of 3 centimeters per second. Making these things up. And we want to find the rate of change of the area of the circle formed with respect to time. So this is a related rates problem, and by related rates it means area is somehow related to time and the radius is somehow related to time. So the rates are related. And what we're going to do here is differentiate with respect to t. So we have our original formula describing the area of a circle. Those two variables, a and r, are related to the third variable, time. So what we're going to do is differentiate with respect to time. So how we do that is so derivative of a is just 1, 1a, derivative is 1, times derivative of a with respect to t. And then pi r squared, remember pi is just a constant, so we have the derivative of this expression, pi r squared, is simply 2 pi r, times the derivative of r with respect to t. So we've just differentiated with respect to t. Now if I want to find the rate of change of area with respect to time, let's say when the radius equals 5 centimeters. We want to find the rate of change of a with respect to time. So we know this to be true. And we just now fill in, no, we want to know derivative of a with respect to t. We know r, which is this, and we know dr dt, or the change in radius with respect to time. It's this, 3 centimeters per second. So simply plugging and chugging, we've got 2 pi times the radius times derivative of r with respect to t. And so the area is changing at a rate of 30 pi centimeters per second. So what that means is when the radius of the circle is 5 centimeters, the area of the circle that it forms is changing at a rate of 30 pi centimeters per second.